Welcome back to che531. In this video, I'll be talking about some symbolic solution using Matlab. I think in the last video I showed some examples using derivatives. This time I'm going to show you some examples using integration. So for symbolic solution, we start by defining the variables like this. So I'm going to introduce a, b, c, and x to be symbols. So we write it as this, symbols a, b, c, x. I define the equation, and then you can solve the equation in terms of x. So basically solve for x given that a, b, and c are known. So this is what we saw last time. Now today we're going to look at how we can integrate a function using symbolic notation. So here I have an example. You can also look at this website where I got most of the examples. So we're going to say x and z are symbols. We're going to define an expression like that is a function of x and, well, it could be function of x and z like this, but for now, let's say it's only function of x. Then you can say integral or int of expression, because there's only one variable x is going to integrate with respect to x. So if I put a breakpoints here and run the code up to there, you should see the result of the integration. So here it is. If this is the function, then the integral would be something like this. And to double check, you can basically take the derivative of that and you should get this function back. Next example is if you want to do integral of f as a function of x and z, but this time we want to integrate with respect to x only, we write it int of f comma x. So if I just run this code for a couple more steps, you see that here it is. So the fx is the solution of the integral with respect to x only. Now, if you want to substitute values in there, we can do it after we integrate. Let's say we get x equal 1, and then the command is going to be subs. So if I do subs, then it's going to substitute the x equal 1 into f of x. So we say subs f of x or fx. We don't need to say anything about x because x is already defined up here. So by doing so, if I go one step down, you should see that if you plug in x equal 1 in there, you get that function. Alright, so another thing that I want to talk about is EasyPlot in Matlab. So EasyPlot is you define a function like this. It's an anonymous function. We call it inline definition. You say f is a function of y, so you write it as equals at, and then parentheses y, and then here's the function. We didn't say what y is, we just said y is a variable. So now in the EasyPlot, I'm going to say what y is going to be. So I'm going to plot f when y varies from 0 to 4. There's no y in here, and I think it's implied. Okay, so implied that f is a function of y and y varies from 0 to 4. And this too means, I believe, let me just run that. Yeah, so I forgot what this too is. But anyway, so it's going to plot f with y varies from 0 to 4, you see that. And then next line is you change the font size to 18 for all the x and y axes. You have an x label of x, y label of f. You can change the font size of x label and y label using the font size. You put a title for your graph, and then you put the grid on. So if I run up to there, then you see now I have my title, the grids are on, so these are the grid lines, and so yes. Okay. There's another way to actually plot the function, and that's you define, let's say, the y, which is a vector from -1 to -0.1 with the separation of 0.01. y2 is this. And then I'm going to create my f of 1 or fy1, which is 1 over y1. Now, because y1 is a vector, we put dot divide by, so this is dot operation. And dot operation means element-wise operation. That means 1 divided by every element of y1. and minus every element of y1 minus 1. So for every element of y1, you get f of y1. And so because y1 has several elements, you also get f of, or fy1 to have several elements. Now you can go ahead and say plot f of, or fy1 as a function of y1. So y1 is going to be on the x-axis, f of y1 is going to be on the vertical axis. The color is going to be blue, because that's what B means, and it's going to be a solid line. So with the dash here, B means solid line with color blue, line width or line thickness of 2. And so if I run that code up to there, you would see that, there you go. It's the line thickness, it's blue, and so forth, right? So in the next command, let's say we're going to put markers for the data points. So if I run that, now you're going to see the markers. And actually, there's one marker here. So what I said was, just draw the 10th element of y1 and 10th element of fy1. Use a marker of dot with red color, and the size of dot is 40. Okay, so what hold on means hold on to the figure, and we want to overwrite or overplot another function on top of it. So the next command we say, okay, now we're going to plot fy2 as a function of y2, solid line, color blue with line width of 2, and again hold on. So we're going to overlay this on the previous plot, and so that's what we get. So there was the first line, there's the second line, the same plot. I'm going to change the x limit from -1 to 2. So if I run that, you see now my x limit is going to be from -1 to 2. And then we're going to set the grid off. So we're not going to see any grid points, or sorry, grid lines. And right. So that's a little bit of intro on how we can use Matlab to do the integration symbolically, derivative symbolically, and do some plots. Alright, so I just remembered what this 2 means. This 2 means actually figure number. So you can there's 2 ways we can say what figure number is. One is we just say figure and then 1. So this is going to generate a window, and it's going to call that window, let's say window 1, and then it plots in that window. Another way is we just say the figure number right here. So I'm saying, hey, go and open a window and call it window 2, and then plot f against y from 0 to 4 in there. So if I run the code, you see that the window number is going to be 2. So here it is, it says figure 2. And if I change this 2 to 3 and stop the code and rerun it, you should see figure 3 there. Oh, not this one actually. Here it is, it's figure 3. This is a different figure, so I have to close this. Okay, this is figure 3. So that number refers to the figure number, right? All right, so now we can go to chapter 2, which is on matrix analysis. So I think in one of the videos before I showed you an example of a sensitive matrix where we changed one of the elements of a matrix by less than 1%, and we saw that the solution changed quite a bit. And we link that behavior to the condition number of matrix A. So here's that example one more time, just quickly go over it one more time. This is a matrix A, and we have a B vector, and then we want to solve AX equal B. So we use / operator to get the solution A / B, we get solution 1, 0. Now we're going to change or perturb one of the elements of the A matrix. Let's say we're going to pick this first one, the element 1, 1, and or maybe no, actually we're going to get the first element of B and perturb it or change it to 4.11. So this is less than 1% change if you compare these two. Right? Now if you go ahead and solve the system again, you get a solution like that, which is completely different from this. So before the first element was 1, second 0, the first one was bigger than the second, and now the first one is smaller than the second. So the reason for this was, if you remember, we linked it to the condition number of matrix A. If you go ahead and calculate the condition number of A, you get something like that. And we said 2000 for condition number is rather big. Condition number is always bigger than 1. So 1 is very well behaved matrix. And as you go up, the matrix become more ill conditioned. Okay, so I think that was a quick review of sensitivity analysis using condition number. Now, there are a few functions that are frequently used in this class. One is norm. So norm, we learned norm of a matrix. I think norm of a vector before. Norm of a matrix is pretty much like the norm of a vector. We had the definition in chapter 1, but in Matlab you can use norm exactly like this word, and then you say matrix A, and then you say what norm you're going to use, 1, 2, or infinity. For infinity, you just type INF. Same thing for the condition number. You can use condition number of A using the p-norm definition. Okay. If the matrix is big and it takes time for Matlab to calculate the condition number, you can use condition or estimate, or use a function to estimate the condition number. And the function to do that is cond_est, which actually estimates the condition number for A. We also have a function to get the reciprocal of a condition number, which is pretty much like determinant. If a determinant is 0 or very small, then the condition number is big. So reciprocal of 1 over, or reciprocal of the condition number, which is big, now it's going to be small. So you can think of 1 over condition number or reciprocal of that. It's pretty much like determinant of a matrix. The function to do the reciprocal of a condition number is rcond. Okay, so a few definitions on matrices. Sparse matrix is a matrix whose most elements are 0. Okay, so if a matrix has a lot of zeros in there, we call it sparse matrix. For any matrix, I can define the density. Density by definition is a number of non-zero A. So these are basically these are exactly Matlab codes. So if you type these in Matlab, you can get the density of a matrix. Anyway, so this is the number of non-zero elements of A divided by the total elements in A. Total elements in A will be the number of rows times the number of columns. So the size of A gives you the number of rows and columns. You get them multiplied by each other. So that's the prod function. Prod gets the product of the row times columns. So this downstairs gives the total number of elements. This is the number of non-zero elements. You divide this by that, you get the density. 1 minus density is defined sparsity. Okay, so here's a quick example for a sparse matrix. Okay, well, actually this is a definition, it's not a quiz, but so a sparse matrix is a matrix whose sparsity is very close to 1. Okay, so if sparsity is close to 1 means density close to 0, means number of non-zero elements is pretty much close to 0. Means most of the elements are 0. We also define bandwidth. So bandwidth of a matrix is the maximum difference between or maximum distance of the non-zero elements from the diagonal. So pictorially, if you have this matrix and I have an element here and an element there, this distance, you find this distance, you find that distance, you do that for every non-zero elements in the matrix, you find the maximum of dij and dmn, that will give you the bandwidth. Okay, so in the next video, we're gonna continue discussion and look at different or special matrices, and at the end, we're gonna look at singular value decomposition. So stay tuned and thanks for watching.